Assalamualaikum warahmatullahi wabarakatuh. We are from the 6th group of Complex Analysis course from International Class Mathematics Education. We want to deliver our material about analytic and harmonic function. The first discussion is talking about analytic function. Let f be a function of the complex variable z. F is analytic at the point z0 if and only if function f has a derivative at each point in some neighborhood of z0. F is analytic in an open set if and only if the function f has a derivative everywhere in an open set. F is entire analytic if and only if function f is analytic at each point in the entire finite plane. Or in other words, function f is having derivative at each point in the entire finite plane. For the cases when the function f is analytic at some point in every neighborhood of z0 except in z0 itself, then z0 is called a singular point or singularity of function f. Let's move to the example. First is fc equal to 1 over z. fc is analytic at each non-zero point in the finite plane since it always have derivative at each non-zero point in the finite plane, with z equal to 0 as singularity of function fc equal to 1 over z. And the second, fc equal to modulus of z is not analytic at any point since it always doesn't have any derivative at any point in the finite plane. And the third, we know that all polynomial function is an entire analytic function since it always have derivative anywhere in the entire finite plane. And the fourth, we have fc equal to square of modulus of z that has no singular point. Now move to the analytic in the domain D. When a function is known as an analytic in the domain D, then the function continues throughout the D, or the function satisfies Cauchy-Riemann equation. So now, to set a function f is analytic in the domain D, we have to satisfy the theorem below. This theorem have been discussed in the previous meeting that talking about the derivative and the continuity in the complex plane. Based on the previous discussion, we know that if we have let f and g be a function of complex variable z and both of them analytic in a domain D, first, we have that the sum and the product of both functions is analytic in the domain D. And the second, the quotient is analytic in the domain D as the function in the denominator doesn't vanish at any point in D, or the denominator does not equal to 0. And the third, the composite of both functions is analytic in the domain D. Now, we have a new theorem that say if f prime z equal to 0 everywhere in the domain D, then fz must be constant throughout the domain D. Let's prove this theorem first. Let fc equal to uxy plus ivxy and assume that f prime z equal to 0 in the domain D. Then based on the Cauchy-Riemann equation, we have that ux plus ivx equal to 0 and vy minus iuy equal to 0. Then consequently, we have that ux equal to uy equal to vx equal to vy equal to 0 at each point in the domain T. Now pay attention to the graph. Along L, that a vector from P to the P prime with U as a unit vector in the direction of increasing S, the directional derivative can be written as the dot product of the gradient of U times the unit vector U, where the gradient of U is equal to uxi plus uyj. Since ux equal to uy equal to 0, then the gradient of U is a zero vector along L. Hence, we have the directional derivative equal to 0, and it means U is a constant along L. Finally, since there is always a finite number of such line segments join end to end, connecting any 2 points P' and Q in the domain T, the values of U at P and Q must be the same. We may conclude then that there is a real constant A such that uxy equal to A throughout the domain T, and similarly we have vxy equal to P, and we find that fc equal to A plus pi at each point in the domain T, which means that fc is a constant at each point in the domain T. Now we have the example of problem. Let's pay attention to the questions. fc equal to z to the power 3 plus 4 over z squared minus 3 times z squared plus 1. Then fz is evidently analytic throughout the z-plane except for the singular points z equal to square root of 3 minus square root of 3 I and the minus I. The analyticity is due to the existence of familiar differentiation formulas which need to be applied only if the expression for f prime z is wanted. The second if we have that fc equal to cosinus hyperbolic x and cosinus y plus I times sinus hyperbolic x times sinus y, that the component function are uxy and then vxy. Because ux equal to sinus hyperbolic x times cosinus y equal to vy, and the uy equal to negative cosinus hyperbolic x times sinus y equal to negative vx everywhere, it is clear from the theorem that the function f is entire analytic.
The next material is about harmonic function. The definition is a real-valued function h of two real variables x and y is said to be harmonic in a given domain of the xy plane if, throughout that domain, it has continuous partial derivatives of the first and second order and satisfy the partial differential equation h xx xy plus h yy xy equal to 0, known as Laplace's equation. And then the next, harmonic functions play an important role in applied mathematics. For example, the temperatures Txy in tin plates lying in the xy plane are often harmonic. A function Vxy is harmonic when it denotes an electrostatic potential that varies only with x and y in the interior of a region of three-dimensional space that is free or charges. And the next is theorem. The first theorem about harmonic function is the first. If a function fz equal to uxy plus ivxy is analytic in domain D, then its component functions u and v are harmonic in D. And then the second theorem is a function fz equal to uxy plus ivxy is analytic in a domain D if and only if v is a harmonic conjugate of u. And then, for the clear understanding, we go to the example. The first example is, it is easy to verify that the function txy equal to a power minus y sin x is harmonic in any domain of the xy plane and in particular in the semi-infinite vertical strip x greater than 0 and x less than p for y greater than 0. It is also assumes the values on the edge of the strip that are indicated in figure below. You can see in the figure that more precisely it satisfies all of the condition t xxxy plus tyyyxy equal to 0. And then we know that t0 y equal to 0, and then t pi y equal to 0, tx0 equal to sin x, and then limit y approach to infinite, txy equal to 0, which describes steady temperatures txy in a thin homogeneous plate in the xy plane that has no heat sources or sinks and is insulated except for the steady conditions along the edge. The next example is since the function fz equal to I over z square is analytic whenever z not equal to 0, and since I over z square equal to I over z square times z bar square over z bar square. And then we do calculation till we get 2xy plus ix square minus y square over x square plus y square square. The two function uxy equal to 2xy over x square plus y square square and vxy equal to x square minus y square over x square plus y square square are harmonic throughout any domain in the xy plane that does not contain the origin.
Okay, I will continue the third part of analytic and harmonic function, that is uniquely determined analytic function. So the first is that there are lemma and theorem. The lemma is suppose that a function f is analytic throughout a domain D, and b fz equals 0 at each point z of a domain or line segment contained in D, then fz equals 0 in D. That is, fz is identically equal to 0 throughout D. So suppose now that two functions f and g are analytic in the same domain D, and that fz equals gz at each point z of some domain or line segment contained in D. The difference becomes hz equals to fz minus gz is also analytic in D, and hz equals 0 throughout the subdomain or along the line segment. According to the lemma, then hz equals 0 through D. That is, fz equals gz at each point z in D. We thus arrive at the following important theorem. So this is the theorem. A function that is analytic in a domain D is uniquely determined over D by its values in a domain or along a line segment contained in D. This is the explanation of the theorem. So the theorem is useful in studying the questions of extending the domain of definition of an analytic function. More precisely, given two domains D1 and D2. Then consider the intersection of D1 and D2. This is the intersection, consisting of all points that lie in both D1 and D2. If D1 and D2 have points in common, and a function f1 is analytic in D1, there may exist a function f2, which is analytic in D2, such that f2z equals f1z for each z in the intersection of D1 and D2. If so, we call f2 an analytic continuation of f1 into the second domain D2. Whenever that analytic continuation exists, it is unique, according to the theorem just proved. That is, not more than one function can be analytic in D2 and assume the value f1z, at each point z of the domain D1 intersection D2 interior to D2. However, if there is an analytic continuation of f3 of f2 from D2 into a domain D3 which intersects D1, as indicated in the figure, it is not necessarily true that f3z equals f1z for its z in D1 intersection D3. Okay, the next is about analytic continuation. If f2 is the analytic continuation of f1 from a domain D1 into a domain D2, then the function f defined by means of the equations fz equals f1z when z is in D1 and fz equals to f2z when z is in D1 is analytic in the union D1 union D2, which is the domain consisting of all points that lie in either D1 or D2. The function f is the analytic continuation into D1 union D2 of either f1 or f2, and f1 and f2 are called elements of f. The next is reflection principle. The theorem in this section concerns the fact that some analytic functions possess the property that fz bar equals fz bar for all points z in certain domains, while others do not. We note, for example, that the function z plus 1 and z squared have that property when D is the entire finite plane. But the same is not true of z plus I and iz squared. The theorem here, which is known as the reflection principle, provides a way of predicting when fz bar equals f of z bar. This is the theorem of reflection principle. Suppose that the function f is analytic in some domain D which contains a segment of the x-axis and whose lower half is the reflection of the upper half which with respect to that axis. Then fz bar equals f of z bar for each point z in the domain if and only if fx is real from each point x on the segment. This is the proof of the theorem. You can pause this video to see the proof. And this is the continue of the proof. You can also pause it here. And this is the last part of the proof of the theorem. Okay, we go to the example of problem. Just prior to the statement of the theorem, we noted that z plus 1 bar equals z bar plus 1 and z square bar equals to z bar square for all z in the finite plane. The theorem tells us, of course, that this is true since x plus 1 and x squared are real when x is real. We also noted that z plus I and iz squared do not have the reflection property throughout the plane, and we know that this is because x plus I and ix squared that are not real when x is real.
That's all the material from us about analytic function, harmonic function, and uniquely determined analytic function. Thank you for watching this video. Don't forget to like, comment, and subscribe. Bye-bye!